This is part 2 of the Permanent Magnet Synchronous Motor Control series with Professor Duco Pule, hardware-in-the-loop application for voltage mode control.
So now we've actually run in simulation this particular model. So if we run this particular model, we can see here, particularly in the XY plot, which is spectacular, it's showing a voltage vector rotate. The switching aspect is not there; it doesn't matter. And this is the voltage blue, and that's the d-axis. So it's a rotating reference frame. So really, what you want to see now is that we get the same thing done in real machines. To do this, we have to then this same controller, this controller here, can be used exactly in the experimental phase. So the next phase we do is going to be here in, that's called lab number 1. C. So now we have a voltage controller here, and in the voltage controller we have the same voltage controller as before, and now we have an additional module which takes the modulation indexes and which does the switching on the actual converter. This is a module which has a physical interface to the actual converter, and the outputs are the voltages from the converter, an alpha beta, and they are the currents, and I can set flags here, these flags, at any point. I've just chosen these 4 here, but I can put them anywhere. I can also put them in here if I needed to look at it. But I can investigate real time any variable at any time. So what we do now is that we have the inputs here, frequency, the 2 voltages. We have a switch here for switch the converter on and off, and we have here a switch which I can select 2 channels of the 4. I have 4 variables I can look at in this. I can make 20, but 4 is enough. I can select between 1, 2, and 3, 4, just because it's chosen to be. And I need to compile this particular model under Tools, Code Gen, and then do compile. And it will generate an output file, which I can then download into the computer, which is what's happening now. And that's been done now. So that's the phase C, as we call it. So we've downloaded that code, and we then run it by moving to C++, which is this lab C++ here. And this is the executable. So this file here is the one we just compiled, and that file here is now going to be run in this particular environment. Now, it has a scope here, and the scope will show you 2 variables, and these are the variables we've just picked up in the previous simulation. So we've set them in the previous simulation. So we're looking at, for example, voltage and currents. And inputs here are the frequency, say 20 Hertz, the voltage, the same reference voltage, 1.5 volts, and then we can run this machine. This is an output showing you the DC bus voltage. It's always a first check to be sure that the DC bus voltage is indeed 24 volts. It's the first check of functioning of the system. These are all the variables we need to set: full-scale voltages, current, frequency, etc. And also here are the converter variables. So let's see what happens now. We have the converter switched off. We don't want it on yet, and we hit the button. And we download again. Now it's 24 volts. We have it set up, and now we can make sure the reference voltage is not too high, 1.5 volts, EQ is 0, and we hit the button. And lo and behold, you can now feel the effect. We are seeing the voltage on this one. If I increase the voltage, the frequency, it will start to spin faster. I mean, if it's 20 Hertz, as it is now, 20 Hertz, it means 300 RPM in this case. If you hold it, you'll see here that you can actually stop it. It's not very robust. And the red is the current, and blue is the actual voltage. Now, that voltage is per unit. So if you multiply it with the scaling value of, in this case, 48, you will see that the 1.5 volts corresponds indeed to that level. So 1.5 volts divided by 48, this is the per unit voltage coming out. So that's the actual voltage level real time of this machine. And this is the corresponding current. This is a current in per unit, it's 0.1. If you multiply it with the full scale values in this case, which happens to be, in this case, 20 volts. So in other words, the current is about 2 amps. So you can see here that this is the first step of it. Now, we've set UD to a certain value. If I set UD down to 0, for example, the voltage becomes less, it won't work. I can increase UQ. And now I've set up UQ, and I can set UD to 0. Exactly the same thing as we did in the simulation. And again, you can confirm operation. And again, you can select different waveforms and look at different at any point, at any time in your converter. And that's the power of VisSim. That is what you can do with no other package. Look at actual instantaneous signals. There is noise on the sampled currents. No problem. You can see it and you can observe it. So that's the first open loop voltage control example of your machine. This is, once you see these waveforms, you basically have a working setup from which to progress into more advanced structures. This is the first step. So the next step will be to do current control. All right, current control.